Hello, I'm Licia Verde, CREA professor at the Institute of Cosmological Science of the University of Barcelona. When I was learning to read, somebody had the brilliant idea to give me a book about the sky. And the book was about everything from meteorology and the birds all the way to the solar system and the universe beyond. And that chapter really fascinated me, and I decided that meteorology was not my thing, but the sky beyond the atmosphere was my thing. It can tell us a lot about the universe in the sense that we can see the universe when it was in a form that was much simpler than it is today. It's a little bit like looking at the picture of a person when he was a baby, and then looking at the photo album of the person all the way to the adult, which is the local universe as we see today, and we can learn a lot about the person, and in the same way we learn a lot about the universe. On top of that, the cosmic microwave background can also act a little bit as a backlight illumination of everything that is in between. So now you can imagine why it was such a pillar for us to understand the composition, the structure, and the evolution of the universe. We know that the universe is expanding. The big revolution, also from the intellectual point of view, which was then recognized with the Nobel Prize in Physics in 2011, was that this expansion is actually accelerating. And it may sound really weird because if there is matter in the universe and matter behaves under gravity, then if I throw something up, I would expect that thing eventually to come down, not if I throw something up to start accelerating up, unless I put an engine to it, but there's no engine everywhere in the universe. So, according to the current best accepted theory of the evolution of the universe started off with a sort of kick expansion in the Big Bang, and then for a while it expanded in a decelerated expansion, as we would expect. But then at some point something happened and this expansion actually started being accelerated, and this is basically what gives all cosmologists a job these days, because it's a really big mystery that we can really can't wrap our head around it. It's about something that is called the cosmic distance ladder. And the cosmic distance ladder is related to the speed of expansion of the universe. So distances in astronomical scale, and even worse in cosmological scales, are very, very difficult to measure because we can't go with a ruler and measure distances as we would do here on Earth. So what we have to do, we have to find either standard candles or standard rulers and then look at them at a distance and then infer the distance that way, as one would do, for example, with the light of a car, that if they are dim, the car is far away, or as our eyes actually do to determine the distance of objects. They use what is called parallaxes, which is the differences in images between the two eyes. But this needs to be building step where each different distance get calibrated on the previous step of the distances. So one methodology is used as to a certain distance. To go beyond that, a different methodology needs to be used, and these two methodologies need to agree and be patched together. And basically that's what the workshop is about, and it has got implication for the expansion history of the universe, because we can measure recession velocity relatively easy and distances are difficult. And the relation between recession velocity and distances is exactly the expansion rate of the universe. Thank you and goodbye.